Okay, folks. Well, we looked at a couple of simple sorting algorithms. I think we looked at bubble sort, insertion sort, selection sort. This time, we want to look at something that's a little bit more efficient in the long run. And this one is called merge sort. And what we're going to do is look at a technique for taking two sorted arrays or two sorted lists and efficiently merging them together into a single sorted list or single sorted array. And then the actual sorting algorithm is going to be based on the idea of, well, if I take my unsorted array or my unsorted list and split it into two unsorted halves and recursively call the sort on each of those halves and then merge those two halves together, then maybe I can come up with a good sorting technique. So it takes this sort of divide and conquer approach where it says, okay, for merge sort as a whole, I'm going to split my array in half, call merge sort on one half, call merge sort on the other half, and then merge those two halves together. Those recursive calls will be doing the same thing. The one that's got one half of the array will be saying, oh, okay, well, I'll call merge sort on my first half and merge sort on my second half and merge those together. And it just continues recursively breaking it down into smaller pieces. Eventually, you get calls where it's saying, we'll call merge sort on just a single element of an array, and that's going to return immediately saying, one element by itself is already sorted. I don't need to do anything. And so we'll take this sort of divide and conquer approach to take an unsorted list or an unsorted array and just keep dividing it in half, calling the function recursively, and then merging the pieces back together to create a sorter bigger chunk, if you will, a sorted bigger chunk. So when we do this, again, we need some kind of an effective merge function. So that's the first thing that we'll take a look at. We need to be able to take two sorted lists or two sorted arrays and efficiently merge them together. And so what we'll do is essentially keep track of where we are in each of these three things. We've got this sorted list or sorted array we're trying to create, and we've got the two sorted portions that we're working with. So I'm going to keep track of what position I'm at in the first sorted one, what position I'm at in the second sorted one, and what position I'm at in this result that I'm building. And then as long as there's still data in both of those two chunks that we're pulling data from, I'm going to say, okay, well, look at the two of them, and whichever one has the smallest value next, we'll take that smaller value. And then we'll advance further into that list. And so we're continually going through saying, okay, well, out of the two of them, what's the next smallest thing? Grab that, move it into the results, bump up where we are in our arrays. So we'll just keep doing that. Eventually, we'll hit the end of one of those lists, and then we'll say, okay, well, everything that's in that other list must be bigger than the stuff we've seen so far. So we'll just move it all across. So this is the general idea we want to aim for. So again, let's say that here's our two arrays or two portions of an array that we're pulling from. So I've got this 10, 20, 30, and I know it's sorted, and I've got this second one, 6, 8, 23, 91. Again, I know these things are already sorted, or I'm trusting that they're already sorted. And so all I'm going to do is say, well, I'm going to keep track of where I am in this one. So at the moment I'm at the beginning, and where I am in this one, and at the moment I'm at the beginning, and where I am in my results, and I'm at the beginning. And I'm just going to compare that next thing in each, the 10 and the 6. What's smaller? Well, obviously the 6 is, so I'll move the 6 into my result and keep track of the fact that I've moved one position further in that second array. So now I've got, I'm at the 10 spot here and the 8 spot here, and I've got the 6 copied into my results. So I compare the 8 and the 10, right? The 8 is smaller, so we're going to move that across, right? So I keep track of the fact, okay, I've moved one spot further in that array, and I've moved my 8 into the results. And I just keep this comparison going. Which is smaller, the 10 or the 23? The 10 is. So I'll move that across and move up one spot in that array, right? The 20 and the 23. Well, the 20 is going to be smaller. So you just keep gradually working your way through the two lists, picking whatever's smaller out of whatever's next in those two lists, moving it across to the other one. And eventually, we'll hit the end of one of these things. Eventually maybe we get to the end of this list, so I've got the 10, 20, and 30, and there's still stuff left in the other one. So at that point, the results in that other one are bigger than everything I've moved so far, so I just keep taking from that second list until I hit the end. So the idea for the merge is relatively straightforward. We can turn that into an algorithm, and then we'll write up the code for that in just a second. Once we've got our merge working, we can take our merge sort by saying, well, if I've got this big array to sort, then I'll break it into two halves, call merge sort recursively on those two halves, and then apply that merge algorithm that we just, or that merge approach that we just came up with, and we're just get my sorted whole, if you like. So I'm going to assume that for merge sort, we're told, here's an array to sort, and here's the positions to work from. So in the beginning, we're going to be working with the whole array, so saying sort from position 0 to size -1. And when I do my recursive calls, I'm going to say, okay, here's the array, but you're only responsible for, this half or this quarter or this eighth, depending on where we are in the algorithm. So if those two positions from low to high, right, if low is greater than high, or then we could ignore it, right? There's nothing to sort. If low is equal to high, we're down to a single element, so we're done. But the general case is going to be, we'll pick kind of the middle position of the array, call merge sort on everything in the low half, call merge sort on everything in the upper half, and then call merge on those two halves. So that'll be the idea for the merge sort. And again, if we've got something like a merge sort with a bunch of scrambled values, it's going to call merge sort on the first half and call merge sort on the second half. Right? So it calls merge sort on that 10, 3. And of course, that's going to go off and call merge sort on its first half and merge sort on its second half. So it calls merge sort on the 10 and calls merge sort on the 3. Those both come back and say, yeah, I'm done. This is just one element. So it gives back a 10 and a 3. We call merge on those, which merges those two sorted portions together to give me the 310. And we get the merge sort call on the second half, which goes through the same sort of idea. It calls merge sort on its first half, right, on the 8, and it calls merge sort on its second half, the 6. And again, those come back right away saying, hey, I am down to one element, I'm done. And so we merge those two sorted portions. We merge the 8 and the 6, and it gives us back the 6, 8. And so now we're back at our top level call to merge sort, right? We've given our 310 back for the first half of this, and we've given our 6, 8 back for the second half of this. And so we call merge on those, and we eventually wind up with our 3, 6, 8, 10 as the sorted result. So again, as far as the algorithm goes, somebody gives us an array, which portion of it we're responsible for sorting. If lower is greater than or equal to upper, no work for us to do, right? We're down to one element or less. Otherwise, we compute the midpoint, call merge sort on the first half, call merge sort on the second half, and then merge those two sorted results together. So we need our merge routine, but we can do this fairly effectively. The one trick here, or the one issue, is that for us to be able to do this, particularly for our merge, we're going to be taking stuff from the lower half of the array and the upper half of the array and trying to write it into that same array, but in kind of merged order. So that gets a little tricky unless we actually create kind of some separate holding space. So as we're going through doing this merge, we'll say, okay, well, I've got 10 values in the first half of the array and 10 values in the second half of the array, and I'll create a temporary array of 20 elements. Put this, as I do my merge, I'll put the results in there and then copy it back into our original as we go. So there is a little extra step involved in creating some temporary storage to hold our results as we're doing the merge, before we can put them back into the original array. But that's not too bad to work through. And so we get this kind of revised version of our merge. So somebody's asking us to, working in this array, we're trying to do a merge of the first half from low to mid with the second half from mid plus 1 to high. And so what I'm going to do is figure out how many values there are in that range, or how big is that space from low to high. I'm going to create a new temporary array of those n elements so it can hold my results, my merged results. I'll go through saying, okay, well, there's still stuff to process in both halves. So while I haven't reached the end of the first half and I haven't reached the end of the second half, I'll take the smaller of the two values, move it into my result, and bump up my positions. And then eventually, once I've merged all of these values into my results array, then I'll go back and copy them back into my original array in the right spots from low to high. And then I can deallocate this temporary array that I created. So that's going to be the algorithm that we're aiming for. Let's see if we can turn that into code. And so we've got our handy dandy merge sort here. And so we're looking at this kind of specialized version of merging where we're saying, okay, here's the array. We're going from position low to high. And in the recursive call, this is the position that they told us they're breaking up at. So my first half goes from low to mid, and my second half goes from mid plus 1 to high. So I'm going to figure out how many numbers there are that I'm merging here. So I'll figure out how big that section of the array is. So it's basically high minus low plus 1. I'll allocate a new array of that size, and hopefully it actually works. If it doesn't work, then we've got memory problems. But assuming it works here, then we can go ahead and say, okay, well, I'll keep track of where I am in the results, where I am in the first half, the lower half of the array, and where I am in the upper half of the array. Right? So starting off at position low in the lower half and mid plus 1 in the upper half. And so while there's still stuff to do in both sides, so while my first half is still at or before the midpoint, and while my second half is still at or before the high end, then I'll figure out which one is smaller, right? Is the one from the first half smaller or is the one from the second half smaller? Move that into my results array and bump up my position in the results array and bump up my position in whichever half I pulled from. Right, so that's going through while there's still stuff to pull from both halves. Eventually, one side or the other is going to be empty, right? I'm either going to hit the end of the first of the lower half, or I'm going to hit the end of the upper half. And once I hit that point, I'll just say, well, grab everything that's left from the side that's not empty yet. So if I haven't hit the end of my first half, then I'll just keep grabbing things from the first half until I do. Or on the other hand, if I haven't hit the end of the second half, then I'll just keep grabbing things from the second half until I'm done. So by the time I've gotten through this, I've moved everything into that temporary array that I created. And so now I want to put things back in the array that they actually passed me. So I'm going to say, okay, well, for every position in my results array, so for every position in that temp array, I want to move it back into a corresponding spot somewhere between low and high. So pause will be where it's going back into in the original array. P is where it's coming from in my temporary array. And we're just going to move everything until eventually we hit the end. And once we get to the end, then we can remember to delete that temporary array that we allocated. So this is going through and actually merging both halves of the segment of the array they asked us to deal with, based on the assumption that those two halves have been sorted by themselves, and we're just trying to merge them together into a sorted whole. So then again, our merge sort algorithm itself will throw in our usual bit of error checking. Okay, if you gave me a null pointer, I can't do anything with it. If there's only one or no elements to sort, then I'm done anyways. But in the general case, I want to figure out where that middle point is, so halfway between low and high. And I want to call merge sort on the first half and merge sort on the second half, and then my merge routine to blend them both together into a result. And hopefully, if we try this out again with our kind of scrambled array here, we'll see if this hopefully produces results from 1 to 16 in sorted order. So we can give this a try. And give it a whirl here. And yeah, looks like we're okay so far. So again, if you want a look at the sample code in a bit more detail, again, it's off the video and slides page. Sample code is linked in the week of February 7th. So you can grab that if you want to have a look at it. And what we'll do next time is do the same sort of thing with a quick look at quicksort.